So in this part, I'll walk you through the geometry conditions, mesh setup, and how to create the actual setup and run the solution. And I'll show you the results, how exactly they have been varied. So first, I'll show you the geometry. So in the geometry, I have created the baffles thing for alternatively using the pattern method, and after that, I have meshed it using Ansys Fluent meshing. Sorry, Ansys meshing. So you can see this is the domain in which the two gases, air as well as benzene, enters from this phase with air as a 0.95 fraction and benzene as a 0.05 fraction, and it comes out of this. And the temperature gradient is given along these walls in the linear way, such that the temperature is varying from 285 to 250 Kelvin up to this line. So from here it is 285 from this line to 250 Kelvin to this line through the profile. Okay, I'll show you the profile also how I've given in the Ansys Fluent UDF. So first, before that, I'll try to mesh this. So you can just have the mesh setup. So this is the mesh setup what I'll be creating. So the default is 0.08. So maybe I will turn it to 0.02. This is an inlet. Sorry, this don't return. I'll just delete and create newly fresh. So this face is inlet. Create neighbor selection. Inlet. This is outlet. And all these faces as a wall. So I'll select Control A and I'll remove this outlet and inlet and I'll name it as wall, to which I'll give the variable temperature profile. So in the mesh, I'll try to create inflation also. First, I'll give a method of multi-zone, right? And to this, I'll also give inflation to the neighbor selection to the wall. Then hit generate. So the mesh is a bit coarser. I'll try to refine. So I'm using a student version, so the node count should be below 512,000. So we'll just check now how exactly it is being generated. I think it's okay. Now we can just check the statistics. It is below the count only, but maybe I can decrease to 5 and I'll just check how exactly it is being. It is taking some time. Yeah, it's a bit finer. It's okay. So now we can see I have created the inflation also to the fluid cells onto the wall surface. Okay. So now I'll close this and I'll go to the setup part. I'll update this. So now before going into the setup of Ansys Fluent, I'll just we have already discussed in the part one that we need to have this supersaturation ratio, and in order to find the nucleation rate as well as critical radius and the changing diameter with respect to the each cell uh, using this criteria. So I'll just walk through the UDF how exactly I've done this. So in order to have the nucleation criteria, this is the macro what we need to use in Ansys Fluent, which is define DPM injection in it, right? So I'm looping through all the particles, and I'm checking for the criteria. If the partial pressure to the saturation pressure is greater than 1, saturation pressure is nothing but the benzene sublimation pressure, and the benzene sublimation pressure is what you are exactly seeing here on this line. So this is the benzene sublimation pressure curve. So these points, all these points on this curve says the benzene sublimation pressure. So you need to check for that. So you can just check using this as a property. What you are seeing here, it is a benzene sublimation pressure with respect to temperature. So when you have the temperature, then you will get the pressure value. So now we partial pressure you will be getting using this function, partial pressure, which is having a C6H6 as the benzene chemical formula that will be going into the setup of Ansys Fluent, and it will gives the value of the partial pressure of the benzene. So that partial pressure of the benzene present in each cell with respect to the sublimation pressure or saturation pressure, if it is greater than 1, then it enters into this loop, and it will run this equation. This is the nucleation rate. That nucleation rate is already present here, which is about a number, and that's equilibrium pressure or the saturation pressure, temperature, saturation, supersaturation ratio, that is. So it all depends on this, and it will help in calculating. And finally I've given that formula directly, and after the calculation, so we'll have a density of the benzene particle which is 1016, and with this critical radius that is already been present here on the screen. I've shown here, this is the critical radius. So it will be calculating this critical radius, and that is being here formulated. You can just check here, and that critical radius, and with the temperature that is present in that cell, with the mass given with respect to the density into the volume of the particle, with the mass flow rate as nucleation rate into the diameters by the time period, that is the time step size, which is 0.001. The time step size is 0.001 second. So this helps in calculating the flow rate of the particles for each cell in 0.001 second, because this formula helps us in giving per meter cube per second the number of particles that have been injected, but we want per 0.001 second. So that is the reason why I have divided by 0.001 second. That helps in giving the particles for 0.001 second. If this is not met, if this partial pressure by saturation pressure is not greater than 0, then there is no flow rate of the particles. That I have given 0 as the flow rate. Now I have also included this DPM switch, where if the particle ratio of partial pressure to saturation pressure is greater than 1, then it will go for DPM user law 1, which is this one, or this law, condense law, in which the particle dia will be increased according to this formula that I've already mentioned on the previous video. So if that is greater than 0, then the extra mass will be added on to the particle with this MP dot, and thus particle will be tracked instead of the previous particle dia. New particle dia will be included and it will be tracked, right? So this defined DPM switch will be switching between two laws. One is in a condense law, other one is simple inert heating of the particle, right? So for each and every step, it will try to calculate using define executed end the pressure ratio, which is partial pressure to the benzene sublimation pressure, which helps in measuring the pressure what we are trying to calculate, right? So this pressure ratio is nothing but the supersaturation ratio, that is S. So that is the final counter. So this is the final counter what you're seeing on the screen. It helps in calculating the supersaturation ratio of exactly it is being contributed. Okay, so now I'll just get into the Fluent setup, and I'll integrate all these UDFs into the setup. So I'll go with 4 cores. It's a student version, so it is limited to 4 cores and 5,000 node as the limit count. So importantly, it should reach the sublimation pressure in order to have the condensation or desublimation from vapor to particles. And it will check for each cell whether the cell is meeting that criteria. Then the particles will be formed, and the particles will grow according to the size what I have given, and the initial particle size will be the critical radius. So now we will go with the transient phenomena with gravity as minus 9.81. So we need to on the species energy as well as species 2. I'm leaving the viscosity as SSTK omega model. So we need to on the species transport, apply, okay. In the discrete phase, interaction with continuous phase, I'll ask it to interact with for every 20 iterations, okay. In the materials, go to the materials tab, go to create fluid database, sorry, the fluid, go to benzene vapor, copy, close. Now go to the mixture template, edit, add air, add benzene, air as last species, remove all this stuff, make it as an ideal gas, and thermal conductivity as well as viscosity also I have done UDFs for those how they behave with respect to the temperature. So this is a benzene air conductivity, mixture conductivity, how it is varying with respect to temperature. So this is the UDF, and this is the benzene viscosity, I mean benzene air combined viscosity, how it is varying with respect to temperature. This is the equation. So dynamic viscosity, how it is being varied. So before that I think we need to compile the UDF. So I'll compile it. This is the UDF. Use built-in compiler, build it. It will show any errors in the compiling stage only. So there are no errors. I'll load it. So these are all the UDFs what I have given. So now I'll just go to this mixture template, and in this I'll use user defined conductivity. Similarly, user defined viscosity. So this is the mass diffusivity of benzene with respect to the air. I will leave it default value, but you can change accordingly if you have the values. So this is nothing but benzene and air. Change create, yes. Close it. Go to the cell zone conditions and verify whether it has a benzene air or not. Yes, it's benzene air. Now you need to go to the discrete phase, go to the injections, create an injection. So it is being shown as anthracite. You can just change from anthracite to benzene particles. So go to this volume injection, and number of starting points is per cell. You can keep 2 as a numbers parcel specification per cell on this entire volume, and your distribution is uniform. So with these diameters and temperature, you need not worry. That will be overwritten what you have mentioned in this UDF. So these are the temperatures and velocities and diameters and density that will be overwritten automatically what is present in the fluid. So I'll be giving a stop time size as 10 seconds. Okay, in the physical model, leave it default. Parse it will be standard. And if you have any turbulent dispersion, you can go with this. So discrete random walk model helps in identifying the stochastic motion of the particles with respect to the turbulence. So how the turbulence will have an effect on these particles, and the probability of those particles with respect to the locations will be integrated using this discrete random walk model if you use. Okay, and then you can go to the UDF with initialization as crystallization. It helps in crystallization UDF with initializing the particle sizes depending on the supersaturation ratio what is mentioned in the UDF. Okay, click OK here, close. So now once the criteria is met, the vapor is turned into particles. So now go to the boundary conditions in the inlet. So I'm giving a mass flow inlet. So go to the mass flow inlet. So with the mass flow inlet, I'll be giving as 0.04 kg per second. Thermal, I'll be giving 285, and with species, I'll be giving fraction as 0.05. DPM is escape. So any particles at the inlet will escape, and at the outlet, So I'll be giving the thermal condition as same 285, and the species 0. Everything is A that is present. It's close, and the wall I'll be giving a temperature profile which is varying from 285 to 250 Kelvin. Go to thermal temperature and give the profile, temperature profile. Okay, apply, close. So now I think everything is intact, and you need to hook that function executed and add. Okay, and I've used two user defined memories to store the supersaturation ratio. So that's the reason why I have increased the UDMs to two variables, two values. Now I'll select 285 as my temperature, which is now present with C6 at 6 as 0 fraction. Nothing is present initially. So these kind of applications will help us to remove the toxicity of the benzene using the cryogenics, and that is application in chemical industry or any other industry. So I'll try to initialize this. So I forgot to give this DPM switch. So you need to go to the injections. So in this custom law, so you need to give the switching DPM switch and try this condense law, and the second law is inert heating. Click OK. And of course you also forgot to give this inert particle as a benzene particle. So it's benzene, sorry, bench particle. The density is 1060, specific heat is 780. Change create, yes. So now again verify whether it is replaced with benzene particle. It's benzene particle. So if it meets the criteria of pressure by sublimation pressure greater than 1, benzene vapor will be now initiated with this benzene particle. According to this UDF, the particles will be injected into the domain. So now we have initialized. Now after initialization, you can just check how exactly the present fractions are there. So maybe I'll select a XY plane, XY plane, create. On this plane you can just check the user defined memory 0. So this is the supersaturation ratio. Now initially it is 0, of course it will be 0. And I'll also create a scene out of this, right? I'll be creating a counter with all this pressure. I'll remove this plane 3, compute save display. This is the pressure initially, and no pressure is present. I mean case pressure is 0. Now I'll also have a particle tracks added with respect to the particle, maybe y velocity. I'll track, no particles present. Don't worry, I'm just creating all this for to create an animation. So after that I'll create a scene out of this with counter to having transparency and activated particle tracks and save display. So now you can see there are no particles, as well as the pressure is 0 gauge pressure. Now I'll try to create an animation for this scene for every 20 time steps or 50 time 20 time steps. Okay, sorry, I'll try to use this current view as my active view. Okay, and I also create another animation with this counter one with 20, and use active view for, sorry, this I think we need to adjust the view here. I'll just go to counter one. I'll just display. Okay, the view is okay now. I'll use the same view. So this gives the supersaturation ratio which is stored in the user defined memory for every 20 time steps. User 2, okay. Now I'll go to run calculation and I'll run some time step. It will take use time. So don't worry, I'll come after maybe 5 or 6 hours. Click on calculate. Or else I'll just run for a few time step and I'll show it to you. But I'll take the animations of all these particle tracks, counters, and I'll just show it to you after 5 hours. Let it run. So right now it has ran through 45 time steps or 0.45 seconds. You can see the counters, the pressure counter, how it is being varying with respect to the time. So, and you can just also see this supersaturation ratio it's near to 0.03 or sorry 0.3. It should cross 1 in order to particles to form. Maybe it will take some time, 4 to 5 hours. I'll just show you the animations after the end of the simulation. Okay, I'll just pause the video now. Yeah, these are the animations. I'll just show you after can just check here. Maybe I'll just minimize this. It's not of that clarity. Okay, right. So you can just check here. The particles are just formed here on this area when the supersaturation ratio is greater than 1 at that point. And now as you progress, more number of particles are being formed. It's enormous number of particles formed, and those are increasing in this velocity with respect to the pressures. Okay. I'll just show you the entire animation without any drop down size. You can see particles are forming here. Yes, the part formed, more number of particles are formed, and they're going out, and some particles have been trapped inside these baffles. It's a continuous process. The particle velocity is continuously varying with respect to the temperature. Temperature profile won't change because it is a linear profile that is varying with respect to the wall. I'll just get with the second animation also. Just show you. You can see. So this is the supersaturation ratio, how it is getting varied. So maybe you will say that it has a red color, maybe it is greater than 1. No, it's not greater than 1. It is 0.7 to 0.8 range. So just show when it is greater than, yeah, now it is greater than 1. At these regions, it is greater than 1, where there is a chance of formation of those particles. And see, you can see here it is more greater than 1, or it is near to 2 also. So more particles will be formed in this region. And that is evident from the previous video also. You can see more number of particles are formed in this region only. And you can see the supersaturation ratio is being greater than 1 continuously at that location only. So we are seeing more particles in that location. Okay. So hope this video has helped you in understanding how the nucleation and growth of the particles occurs in the cryogenics part of CFD simulations. Thank you.